Introduction: the giant's disappearance. Imagine, for a moment, that the largest planet in our solar system, Jupiter, vanished without a trace. One instant, it's there, looming as a colossal guardian with swirling storms and color more than 300 times that of Earth, and a gravitational pull that has shaped the architecture of our solar system. Its role is far more profound than we usually consider. It's a gatekeeper, a protector, a gravitational anchor, and perhaps even a reason life could thrive on our pale blue dot. This audiobook gently takes you on a journey through the hypothetical scenario of Jupiter's sudden disappearance. Each chapter explores different consequences, from shifts in orbital dynamics and the fate of the asteroid belt, to the long-term implications for Earth's climate and the delicate balance that keeps our solar system in harmony. Whether you're a curious mind looking to explore cosmic possibilities, or simply yearning for a relaxing voyage through celestial what-ifs, this story unfolds like a thought experiment wrapped in the quiet wonder of space. So, settle in, dim the lights. Let your mind float beyond the sky. Together, we'll explore what might happen if the mighty Jupiter were no more. Chapter 1: The Sudden Silence. Jupiter disappears. The night sky remains unchanged at first glance. Stars still twinkle across the black canvas. Constellations trace familiar paths. And the moon gently rises in its age-old rhythm. But for those who know where to look, something is missing. Jupiter, the mighty beacon, often visible to the naked eye, no longer glows in its corner of the cosmos. It has vanished. And with it, a profound silence begins to creep through the solar system. The idea is staggering. Jupiter, a planet so massive it could contain all the others combined, excluding Saturn, has disappeared. There's no explosion, no celestial debris, no gravitational shockwave that knocks satellites from the sky. Just an absence, as though someone had erased a giant brushstroke from the solar system's masterpiece. Almost immediately, the solar system begins to feel this change, not in dramatic chaos, but in subtle alterations. Jupiter's gravity, once a stabilizing force, had been holding many things in place. It acted as a shepherd for asteroids, a deflector of comets, and a balancer of planetary orbits. Without it, the equilibrium begins to loosen, like tension releasing from a tightly held string. Let's consider the orbital ballet of the solar system. Each planet, from tiny Mercury to icy Neptune, moves in a delicate gravitational interplay, pulled by the sun, nudged by each other, and most notably, influenced by Jupiter's immense presence. When Jupiter vanishes, Earth doesn't careen into chaos immediately. It continues its orbit, seemingly untouched. But the gravitational conversation that has echoed for billions of years is now missing a voice, and the silence it leaves behind is more dangerous than noise. Mars, our red neighbor, begins to drift ever so slightly. Its path, once subtly shaped by Jupiter's mass, begins to wobble. Saturn, no longer kept in line by its big brother, experiences minor shifts in orbital timing. These are imperceptible over days or even years, but over centuries, they could grow into resonant effects enough to tilt the architecture of the solar system into unfamiliar geometries. Perhaps the most immediate consequence is not felt on Earth, but in the asteroid belt between Mars and the now lonely Saturn. It stirred the rocks, kept them moving chaotically, and prevented their union. Without Jupiter's interference, the dynamics of the asteroid belt begin to change. Collisions become less frequent, but more dangerous. Some asteroids begin to drift, no longer tethered by Jupiter's influence, becoming wandering threats. And then there are the comets. Jupiter has long been considered Earth's celestial shield, intercepting or deflecting objects from the outer solar system that might otherwise barrel toward us. The so-called cosmic vacuum cleaner effect of Jupiter is more than poetic. It's based on observable events. Shoemaker Levy 9, a comet that shattered and crashed into Jupiter in 1994, served as a stark reminder of the gas giant's role as a planetary protector. Without it, Earth may find itself exposed, vulnerable to debris that once had a 50-50 chance of being consumed or flung away by Jupiter's gravity. This is where subtlety ends and long-term consequences begin to shimmer on the cosmic horizon. With Jupiter gone, the Kuiper Belt, home to icy bodies like Pluto, Eris, and Haumea, loses a key enforcer of stability. Orbital resonance between Jupiter and many of these distant objects ensured a level of predictability. Now, those resonances are disrupted. The distant solar system begins to churn. Small changes begin to amplify. A kind of orbital unrest is unleashed, imperceptible at first, but increasingly chaotic. Meanwhile, Earth continues its spin, its tides rising and falling with the pull of the moon. To humanity, nothing has changed, yet scientists will begin to notice discrepancies. Calculations about satellite orbits drift off course. Probes once influenced by Jupiter's gravity no longer follow predictories. Astrophysicists, who rely on the gravitational pull of Jupiter to slingshot missions into deep space, suddenly lose one of the most valuable tools in interplanetary navigation. The sudden absence of Jupiter is not like removing a tree from a forest, is more like removing a dam from a river system. The flow continues, but everything downstream is eventually altered. Currents change, erosion begins, and new paths are carved where none were before. Within a few years, simulations begin to diverge from reality. Computer models of the solar system's future, once stable for millions of years now, show chaotic outcomes. Some planetary orbits begin to exhibit minor but increasing eccentricities. Earth's climate, delicately linked to orbital stability, may one day feel this in the form of altered Milankovitch cycles, which influence glacial periods and global temperatures. This, of course, would take tens of thousands of years, but the seeds of change are already planted. Jupiter's disappearance is like a cosmic ghost, silent, invisible, but deeply felt. And perhaps the strangest aspect of all is how easily life on Earth continues, unaware of the slow destabilizations set in motion beyond the sky. Civilization marches on, oblivious to the gravitational tapestry that once held the solar system together, with invisible threads of order. What does this mean for the long-term survival of Earth? What new threats may emerge from the deep reaches of space now unguarded? And how does the solar system adapt to this vacuum of power? In the next chapter, we venture deeper into the aftermath, to the region known as the asteroid belt, where thousands of rocky bodies begin to feel the absence of their ancient warden. The question becomes not just what will happen, but when. Chapter 2: The Stirring Stones. Chaos in the asteroid belt, deep between the orbits of Mars and the now untethered Saturn, lies a vast region filled with cosmic debris. Asteroid belt. To most, it's a quiet, uneventful place. Billions of rocky fragments drift in isolation, leftovers from the early formation of the solar system. But behind that apparent stillness lies a fragile equilibrium without being destabilized. These empty corridors, known as Kirkwood gaps, were direct consequences of Jupiter's influence, acting like silent boundaries etched across space. Now, those boundaries dissolve. The first effect is subtle. Orbital resonance vanishes. Without Jupiter's constant tug, the asteroids begin to shift into once forbidden zones. Areas that were previously devoid of rocks become populated. But this isn't peaceful migration, it's disordered chaos, with new gravitational interactions emerging and the loss of Jupiter's regulating pull. Collisions become more frequent. Massive fragments crash into one another, breaking into clouds of debris. The asteroid belt becomes increasingly volatile. From Earth, we see none of this. But space telescopes pointed toward the belt would detect unusual increases in infrared light that glow. It's the signature of dust clouds forming from high-speed collisions, a sign that the solar system's rocky graveyard is waking up. Some asteroids, now liberated from their old orbital prisons begin to drift outward. Others spiral slowly inward, crossing Mars' path. The planet, which had once lived near this rocky boundary without major incident, now faces more frequent encounters. Small impacts, its surface, new craters forming over time. While Mars has no atmosphere to protect it, Earth still does but. That won't be enough forever in the newly unstable belt. A particularly dangerous class of rocks begins to emerge: planet crossers. These are asteroids whose altered orbits now intersect those of the inner planets, especially Earth. Previously, Jupiter's gravity had either captured or ejected many of these potential threats. It kept the belt largely confined, acting like a shepherd dog around a herd. And the predators are loose. These rogue asteroids are not large enough to destroy planets, but some are significant enough to cause regional catastrophes if they strike Earth. Think of the object that likely ended the reign of the dinosaurs Chicxulub. It was around 10 kilometers wide. There are dozens of similar-sized bodies in the asteroid belt, and without Jupiter to influence their fates, the statistical likelihood of an impact event increases significantly. More concerning still is the long-term dynamic evolution of the belt. Without Jupiter's stabilizing resonance, many of the larger asteroids begin to shift slowly into chaotic orbits, influenced now more by Saturn, Mars, and even Earth itself. These interactions create unpredictable trajectories. Some are ejected entirely from the belt, while others find themselves locked in deadly paths toward the inner solar system. Earth's scientists, watching these events unfold over years and decades, begin to detect an uptick in near-Earth objects, NEARs. Their instruments report more frequent, close approaches, asteroids passing within a few 100,000 kilometers of Earth. The sky, once calm, is now more crowded with objects that move fast and behave erratically. But not all consequences are destructive. Some asteroids, freed from the gravitational traps of the belt, begin to collide and fuse over millions of years. New protoplanets might begin to form, a process that was previously impossible under Jupiter's interference. This chaotic freedom could slowly transform the belt into something more cohesive, a site of new planetary birth. Ironically, Jupiter's absence may allow a planet to form where none could before. Yet, in the short term, danger outweighs creation. Space agencies grow increasingly concerned. The models they once used to predict asteroid movement no longer align with reality. New algorithms must be developed. New warning systems must be put in place. And with every decade that passes, the odds of a significant impact event creep upward. Meanwhile, Saturn begins to take on a new role, perhaps reluctantly. With Jupiter gone, it becomes the most massive planet in the solar system. But Saturn's gravity, while strong, is not positioned to serve as a protective gatekeeper in the same way. It lies too far from the asteroid belt to exert consistent control. Its orbit is also more inclined, meaning it can't sweep the belt effectively. Saturn is a silent monarch, but not a defender. In the background, Earth's moon also plays a part. It quietly influences some of the near-Earth asteroids through lunar-assisted gravitational shifts, but even combined with Earth's own pull, this defense is minuscule compared to the shielding that Jupiter once provided. The solar system is becoming more porous. In mythology, Jupiter was king of the gods. In astronomy, it was king of gravity. Without it, the solar system is exposed, no longer protected by the massive presence that deflected, trapped, and absorbed countless cosmic threats. The asteroid belt, once locked in place, becomes a brewing storm. In the next chapter, we'll turn our attention to the outer solar system where icy worlds beyond Neptune begin to experience their own unraveling. With Jupiter gone, the far reaches of our planetary family start to drift. The question no longer is just about what falls inward, but what begins to slip away. Chapter 3: The Outer Drift, Unraveling the Kuiper Belt. Far beyond the terrestrial planets and the ghostly haze of the asteroid belt, the solar system continues into darkness. Here lies the Kuiper Belt, a vast and frozen region filled with icy remnants from the early solar system. It stretches beyond Neptune's orbit, a cold frontier populated by dwarf planets like Pluto, Haumea, and Makemake, along with countless smaller, icy bodies. This distant zone has long been a quiet realm, cold, slow-moving, and seemingly detached from the inner solar system's turbulence. But even here, Jupiter's gravitational influence was quietly at work. Though separated by immense distances, its presence helped define the very structure of this region. It shaped orbital resonances, dictated the migration of giants, and played a role in sculpting the fate of the outer planets. With Jupiter gone, the unraveling begins slowly, subtly, but inevitably. One of the first regions to feel this shift is the resonant population of Kuiper Belt objects, KBOs. These are bodies whose orbits were in precise ratios with Jupiter and Neptune. For instance, Pluto orbits the Sun twice for every 3 orbits of a Neptuna configuration, made stable in part due to the ancient migrations of the giant planets, where Jupiter's gravity played a balancing role. Without Jupiter's gravitational hand in that early ballet, these resonances begin to weaken. The orbits of some KBOs drift ever so slightly. their precise timing disturbed. Over thousands of years, small discrepancies grow larger. Some objects begin to fall out of resonance altogether, their paths wobbling into more eccentric or inclined orbits. As the delicate web of orbital relationships starts to loosen, a new kind of disorder emerges. One key effect of Jupiter's early role was in setting the architecture of the outer solar system. When Jupiter and Saturn migrated inward and outward during the early days of planetary formation, their combined gravitational resonance swept migrations loses its coherence. It's as if a massive anchor has been pulled from a mobile. The balance shifts, and the pieces start to drift. Large KBOs like Eris, Sedna, and Orcus begin to experience tiny changes in their trajectories. Their interactions with Neptune become more pronounced. With no distant gravitational check from Jupiter, these outer bodies feel a subtle pull toward chaos. It's not sudden, it's glacial. But over millions of years, more and more objects begin to meander from their familiar lanes, like travelers on a snowy plain with no road signs. Some are pulled inward, others are pushed outward, escaping slowly into the deeper darkness of the scattered disk, and eventually into the Oort cloud. A few become interstellar travelers, ejected entirely from the solar system, destined to wander alone through the void. Meanwhile, Neptune, now the outermost major planet, takes on a heavier gravitational load. In the absence of Jupiter, its interactions with the Kuiper belt become stronger. But Neptune, elegant as it is, lacks the sheer mass to regulate so many objects. The belt begins to swell in dynamical activity. New collisions occur. Some icy bodies are disturbed just enough to fall into long looping orbits that stretch toward the inner planets. This raises another concern: Centaur objects. These are icy bodies that drift from the Kuiper belt into the space between Jupiter and Neptune, often becoming short-period comets. With Jupiter absent, more of these icy wanderers find their way inward. But there is no longer a giant planet to deflect or capture them. Instead, they sail into the inner solar system unimpeded, occasionally passing near Earth's orbit. Some of these centaurs become active comets, developing glowing tails as they approach the sun. Their frequency increases, and their behavior becomes less predictable. Earth's skies grow more dramatic, bright streaks of icy visitors gracing the heavens. Beautiful, yes, but also a sign of a solar system slipping into greater disorder. Astronomers begin to notice another trend: increased gravitational perturbations in the trans-Neptunian region. Some theories that once posited the existence of a hidden planet gain renewed attention. Without Jupiter's gravity to mask or absorb minor disturbances, distant anomalies in orbital motion become more evident, whether Planet 9 exists or not. The solar system's outer edge now seems more alive with motion and mystery. But not all is destruction and danger. This great shifting may also give rise to new interactions, KBOs pairing off into binary systems, forming temporary moons or orbitals. The outer solar system, once a realm of frozen predictability, becomes a laboratory of evolving gravitational experiments. For Earth, the immediate effects remain distant, crashing asteroids or rogue planets threaten the biosphere just yet. But the long-term implications are clear. The cosmos is shifting, slowly but irrevocably. The celestial dance that held for billions of years is now improvising, creating new steps without its strongest lead. The Kuiper Belt, once overlooked, now stands as a place of dynamic intrigates, icy silence broken by motion, collision, and migration. In the next chapter, we travel even farther to the edge of the sun's influence, into the ghostly realm of the Oort cloud, where long-dormant comets may now awaken. The absence of Jupiter reverberates even there, where the sun becomes little more than a distant lamp, and where the most ancient messengers may now begin their long descent inward. Chapter 4. The Awakening Halo echoes in the Oort cloud, at the very edge of the solar system, where the sun's light is no more than a pale glimmer and space begins to merge with the interstellar medium. Least understood regions of our cosmic neighborhood. The Oort cloud. It is not a flat disk like the Kuiper Belt, but rather a vast spherical shell, a halo of icy bodies orbiting the sun from every angle, surrounding the solar system like a cosmic cocoon. Here, the temperatures are close to absolute zero. The objects are ancient, frozen relics from the birth of the solar system, untouched for billions of years. Their orbits are staggeringly vast, some requiring hundreds of thousands or even millions of years to complete a single circuit around the sun. They drift silently, slowly, and alone. For the most part, they are forgotten. But even in this distant realm, Jupiter's gravity played a crucial role. Throughout the solar system's history, Jupiter acted as both a gatekeeper and a slingshot. When comets from the Oort cloud wandered inward, Jupiter either captured them, flung them into deep space, or redirected them into harmless orbits. In fact, many of the long-period comets that we observe from Earth originated in the Oort cloud and were only able to reach us because of gravitational nudges from Jupiter and the other giants. Now, with Jupiter gone, a silent and profound change begins to take place in this icy sphere. The first sign is an increase in gravitational noise, not literal sound, but the slight, unpredictable perturbations that result from the shifting mass distribution in the inner solar system. The Sun, of course, remains the dominant force, but the absence of Jupiter's mass causes subtle changes in the overall gravitational shape of the system. Many Oort cloud objects, already delicately poised on the edge of solar gravity, respond to this change. Their orbits stretch, tilt, or collapse inward. Some begin the long fall toward the Sun, entering the solar system as new, unpredictable comets. Others are destabilized just enough to be nudged by passing stars or interstellar currents, forces that Jupiter's gravitational echo once softened. As a result, the inner solar system begins to receive more frequent visits from these ancient travelers. Long-period comets, typically rare, arriving once every few decades or centuries, now appear in the sky with greater regularity. Their tails grow bright as they near the Sun, spraying dust and gas across the heavens. To the casual observer, it's a beautiful phenomenon, but to astronomers, it's a troubling omen. The Oort cloud is awakening. This increase in cometary activity poses new risks. Unlike asteroids, which generally follow more predictable paths, long-period comets often arrive with little warning. Their orbits are highly eccentric, and they move at incredible speeds. A single miscalculation, or even a small observational error, can leave humanity exposed to a high-velocity impact. Jupiter once served as a deflection barrier. Its strong gravity would either capture inbound comets or alter their trajectories before they could reach the inner planets. With it gone, Earth's line of defense is significantly weakened. Historical records remind us just how dangerous these objects can be. The Tunguska event in 1908, while likely caused by a much smaller body, perhaps a fragment of a comet, demonstrated the devastating potential of even minor cosmic visitors. An actual impact from a full-size Oort cloud comet, kilometers wide and moving at tens of kilometers per second, could cause a global catastrophe. But beyond the threat, there's also a strange beauty to this cosmic shift. Some astronomers suggest that the increase in comet activity might bring with it scientific opportunities. These comets are time capsules carrying pristine materials from the solar system's earliest days. As more of them enter the inner solar system, robotic missions could be sent to sample, study, and even mine them. They offer insight into the origins of water, organic molecules, and possibly the very ingredients of life. Yet, even in this optimistic light, the broader picture remains one of a solar system drifting toward chaos. The Oort cloud, once held in loose harmony by the gentle pull of the Sun, and the watchful eye of Jupiter becomes a far more dynamic region. In the long term, its instability could lead to the loss of many of its objects, some flung out into interstellar space, others drawn too close to the Sun and consumed. It may slowly erode, like a glacier exposed to warming air. Meanwhile, the Sun continues to shine, oblivious to the shifting tides of gravity that stir in its orbiting halo. Earth. Still, a blue jewel nestled in the habitable zone grows more vulnerable. Not immediately, but with every passing millennium, the odds tip. The sky becomes busier. Comet paths grow harder to predict. Impact probabilities rise, and all because one giant Jupiter has vanished. In the next chapter, we'll turn our gaze inward once again, this time to the gas giants that remain. With Jupiter gone, Saturn, Uranus, and Neptune begin to dance differently. Their movements, once harmonized by Jupiter's immense pull, now begin to shift in subtle but important ways. We will explore what happens when the gravitational leader is lost and what new chaos may emerge among the remaining giants. Chapter 5. The Giants Rebalance. Saturn, Uranus, and Neptune without their leader in the grand hierarchy of the solar system. Jupiter was more than the largest planet. It was the gravitational core around which the dance of the gas giants was choreographed. Its mass, over twice that of all the other planets combined, gave it a quiet dominance. When Jupiter moved, the rest responded. With its disappearance, a strange stillness follows, but not for long. Now, in the silence left behind, Saturn finds itself elevated to the role of the most massive planet. Yet the crown it inherits is both symbolic and hollow. Saturn, beautiful and enigmatic with its magnificent rings, was never built to lead. Its influence extends only so far, and its orbital characteristics lack the stabilizing gravity that Jupiter once provided. The first change begins with orbital timing. For billions of years, Jupiter and Saturn existed in a gravitational relationship called mean motion resonance. Although not locked into a tight pattern like some moons are with their host planets, the giants exchanged gravitational tugs that helped prevent chaotic drift. Without Jupiter's subtle but constant nudges, Saturn begins to experience orbital precession, a gradual wobble in its elliptical path around the Sun. At first, these variations are tiny. In fact, for human lifespans, they remain invisible. But on cosmic timescales, they build. Saturn's path may stretch slightly, become more eccentric, or tilt incrementally. This has consequences not just for Saturn itself, but for the entire balance of the outer solar system. As Saturn shifts, its own influence over Uranus and Neptune becomes more pronounced. but it is an imperfect fit. The spacing between these giants was once regulated in part by Jupiter's distant pull, keeping their interactions relatively mild. Now, Saturn's adjusted orbit occasionally resonates more strongly with Uranus, initiating a slow, gravitational dialogue that wasn't there before. Uranus, a planet already tilted dramatically on its side, responds with its own adjustments. Over time, its orbital inclination may shift, or its rotation may begin to experience minor perturbations. These changes are subtle, but they ripple outward. Neptune, cold and distant, remains mostly isolated. Its orbit is far enough from Saturn that immediate interactions remain weak. But even here, the gravitational shift makes itself known. Neptune's long-standing resonance with Pluto and other trans-Neptunian objects begins to unravel slightly as the outer solar system becomes more dynamically active. An important consequence of this domino effect is the potential for orbital resonance overlap. This phenomenon in celestial mechanics can lead to chaotic motion. When the regular gravitational influences of large bodies begin to interfere with one another instead of reinforcing stable patterns, orbits can become unpredictable. Over tens of millions of years, this could lead to close approaches or even planetary migrations. While the idea of planets colliding is the stuff of science fiction, close interactions could indeed happen on extremely long timescales. These wouldn't involve crashes, but rather gravitational assist giant planets slinging each other into new orbits. Such a shift could send Uranus inward or cause Neptune to drift slightly outward. Even small changes in position can have cascading effects on moons, rings, and surrounding debris. Another often overlooked aspect is the gravitational impact on Saturn's ring system. The rings are composed of countless particles orbiting in precise harmony, their structure maintained by a combination of Saturn's gravity and the influence of its many moons. But Jupiter's gravitational presence far away, though it was helped suppress small perturbations from other sources, contributing to the long-term stability of the system. Without Jupiter, these external perturbations have more freedom to act. Interactions from the Sun, passing objects, and even Saturn's own moons may have greater impact. Over long periods, this could lead to structural changes in the rings. They may become more diffuse, begin to fragment, or collapse into Saturn itself. The most iconic feature of the second largest planet may not last forever. The removal of Jupiter also affects the migration history of these planets. Some planetary scientists believe that Uranus and Neptune were once much closer to the Sun, and that interactions with Jupiter and Saturn pushed them outward to their current positions during the early solar system. With Jupiter now gone, any residual gravitational echoes from those migrations are severed. long-term orbital models must now be rewritten. There's also the psychological aspect. How humanity perceives this new arrangement for centuries. Our understanding of the solar system has been grounded in a framework with Jupiter at the heart of planetary dynamics. Without it, astronomers must reconsider models for planetary formation, migration, and resonance. It's a scientific revolution that may echo the Copernican shift, forcing a re-evaluation of the forces that shaped our cosmic home back on Earth. These changes remain invisible. Saturn still glows softly in the night sky. Its golden hue, a beacon for backyard astronomers. But behind the scenes, the harmony of the outer solar system has shifted. It is now a looser symphony, more improvisational, more vulnerable to dissonance. And what of the moons? Titan, Enceladus, Miranda, Triton. These satellites, many of which harbor oceans beneath their surfaces, may now find their tidal environments slightly altered. Tiny changes in orbital eccentricity can affect internal heating, possibly shifting the prospects for life in these hidden worlds. The solar system is beginning to feel adrift, with the gas giants adjusting to their new gravitational roles, and the inner planets still oblivious to the changes beyond the asteroid belt. A slow rebalancing is underway. In the next chapter, we journey back toward the inner solar system to see how Jupiter's absence begins to alter the dynamics of Earth, Mars, and Venus. Though the effects are slower and subtler, the seeds of future instability are already being sown. What happens when the gravitational scaffolding of the solar system weakens? With a bang, but with a whisper. Chapter 6. The subtle shift. Earth and the inner planets feel the echo. For a while, Earth continues in blissful ignorance. The sun still rises. Seasons turn. The moon traces its ancient path across the sky. Life on the surface is undisturbed, but in the vast quiet of the cosmos, balance is no longer what it once was. And the inner planets are beginning to feel it. The solar system is a system in the truest sense of the word. Every object, every orbit, every mass is interconnected. Jupiter, with its immense gravity, exerted not just force, but order. Even the terrestrial planets, though far less massive and much closer to the Sun, existed within the framework Jupiter helped maintain. Now, the invisible scaffolding begins to loosen. The first sign is not dramatic. Earth's orbit remains stable at least for now. But Jupiter's influence wasn't about day-to-day stability. It was about long-term resonance. One of the most important ways this influence manifests is in the regulation of Milankovitch cycles, the long-term variations in Earth's orbit and tilt that affect climate over tens to hundreds of thousands of years. These cycles are governed by three main factors: eccentricity, obliquity, and precession. Jupiter had a major role in stabilizing the eccentricity of Earth's orbit, how stretched or circular it is. Without Jupiter's gravity acting as a brake on those variations, Earth's eccentricity may begin to vary more dramatically over long periods. The result? A planet that swings farther from or closer to the Sun during its orbit, intensifying the effects of ice ages and warm periods. Climate scientists looking at ancient ice cores and ocean sediment records would notice a change. Patterns that once followed a predictable rhythm begin to drift. Glacial cycles become more erratic, with longer and harsher ice ages or abrupt warmings. These shifts could disrupt ecosystems, challenge agriculture, and accelerate the pace of natural climate change, well beyond anything previously experienced in the Holocene. But the story doesn't end with Earth. Mars, the red world, is perhaps even more sensitive to Jupiter's loss. As the planet closest to the asteroid belt, Mars relied on Jupiter's stabilizing influence to keep the chaotic gravitational tides at bay. With Jupiter gone, Mars is now subjected to increased perturbations from drifting asteroids and from Saturn's slowly shifting gravity. Its orbit begins to wobble. Not enough to eject it from the solar system, but enough to make its path increasingly eccentric over millions of years. This makes Mars periodically colder, or alternatively, warms it just enough to trigger sublimation of polar ice. Dust storms grow more frequent and chaotic. Mars' fragile atmosphere, already tenuous, may lose the last of its seasonal consistency. More troubling is that the eccentricity of Mars could, over vast spans of time, bring it into more direct gravitational interactions with Earth. Astronomical models suggest that even slight instabilities multiplied over eons could eventually create orbital overlaps or close approaches between Mars and Earth. The risk is not collision, but resonant instability where gravitational nudges slowly amplify each other, possibly threatening Earth's own long-term orbital path. Venus, though closer to the Sun, is not immune either. Its rotational ready strange, slow, and retrograde, sensitive to gravitational influences. Jupiter once provided a stabilizing tug on the orbital relationships between Earth and Venus, helping to maintain their current spacing and resonance. With that tug missing, Venus may slowly shift its orbital eccentricity, slightly altering its relationship with both Earth and Mercury. These shifts are not quick. They are not explosive, but they are relentless. Another fascinating consequence concerns Earth's axial tilt. While most of the tilt is controlled by the Moon, our primary stabilizer, Jupiter, provided additional gravitational buffering that limited wild oscillations. Without it, Earth's axial precession may become more extreme, possibly leading to larger seasonal swings over millennia. This would mean greater contrasts between summer and winter, altering the evolution of life and perhaps forcing entire ecosystems to migrate or collapse. Meanwhile, the moon, our ever-watchful companion, continues its slow recession from Earth. But even this dynamic is now slightly altered. As the Sun and the remaining planets adjust to the new gravitational configuration. Over millions of years, tidal interactions, climate feedback loops, and orbital precession become increasingly unpredictable. It's important to understand that while these changes are slow, their cumulative effect is vast. Earth has enjoyed a rare stability in its orbital and climatic patterns for billions of years, a Goldilocks period that allowed complex life to evolve. With Jupiter's absence, that stability is no longer guaranteed. Imagine a future Earth in which the length of seasons begins to vary unpredictably. Ice ages that last tens of thousands of years give way to sudden global thaws. Rainfall patterns shift dramatically. Ocean currents, driven by temperature gradients, begin to behave erratically. Over time, this could reshape continents, displace civilizations, and rewrite the course of life on the planet. But there's another element at play: the increased flux of impact threats from the destabilized asteroid belt. Earth's atmosphere and biosphere now face a higher likelihood of being struck by celestial objects. These are not everyday dangers, but with Jupiter gone, the background risk has permanently increased. The sky, once a source of awe and constancy, becomes a little more uncertain. Astronomers tracking Earth's long-term trajectory begin to see deviations in orbital models. Calculations once thought reliable for 1 billion years into the future now diverge at earlier points. The simulations, now lacking Jupiter's stabilizing mass, show greater orbital chaos, especially in the distant future. And yet, amid all this, Earth still spins. The sun still warms the oceans. Flowers still bloom, unaware of the subtle unraveling in the heavens. In the next chapter, we'll explore a very human question. What would the loss of Jupiter mean for space exploration and science itself? The technological future of Earth is tied to gravity, the slingshots we rely on, the missions we launch, and the models we use. Without Jupiter, the very way we navigate the cosmos will need to change. Chapter 7: Lost Slingshots. Space exploration without Jupiter. For decades, humanity's dreams of venturing beyond Earth have relied on a combination of innovation, mathematics, and a deep understanding of gravity. In this cosmic game of interplanetary travel, one tool has proven especially invaluable: the gravity assist. And no planet has served this role more effectively, more reliably, or more often than Jupiter now. That tool is gone. Jupiter's disappearance marks more than just a gravitational imbalance. It also severs a vital component of how we explore space. From the earliest interplanetary probes to the most ambitious missions of tomorrow, Jupiter's immense mass has acted as a kind of celestial springboard, allowing spacecraft to gain momentum and reach destinations that would otherwise require far more fuel and time. The famous Voyager missions are perhaps the clearest example. Launched in 1977, both Voyager 1 and Voyager 2 used Jupiter's gravity not just to study the planet itself, but to accelerate outward to Saturn, Uranus, Neptune, and ultimately the edges of the heliosphere. Without Jupiter's massive gravitational pull, these missions would have been impossible in their current form. They would have required massive onboard propulsion systems or decades more to reach their targets. With Jupiter gone, the rules of deep space travel are rewritten. One of the first and most profound consequences is the loss of a major gravity assist point. Space agencies planning missions to the outer planets, the Kuiper Belt, or interstellar space must now calculate new trajectories using less efficient routes. This means longer missions, greater fuel requirements, and increased costs. In some cases, destinations may be rendered inaccessible with current propulsion technologies. Even missions that never intended to reach Jupiter often depended on it indirectly. Trajectory planning is an intricate puzzle, and Jupiter has long served as a key piece event for missions that only passed near its orbit en route to other planets. Its gravity provided flexibility, allowing mission designers to fine-tune paths and timing in ways no other planet could replicate. Saturn, while massive in its own right, is not a suitable replacement. It's farther from the Sun, less accessible for quick flybys, and less frequently aligned with Earth for optimal launch windows. Its gravitational influence, while strong, is simply not in the right place to serve as a reliable assist point for most missions. In addition to propulsion challenges, there's a more symbolic and scientific loss. Jupiter was a science destination in its own right. The planet's complex atmosphere, powerful radiation belts, swirling storms, and magnetosphere made it a natural laboratory for understanding gas giants, planetary formation, and even the behavior of exoplanets. With it gone, humanity loses an irreplaceable testbed for planetary science. Generations of data collected from flybys, orbiters, and probes like Galileo and Juno now become historical records of a world that no longer exists. Moreover, the Galilean moons Hue, Europa, Ganymede, and Callisto were among the most intriguing bodies in the solar system. Europa, in particular, harbored a subsurface ocean that many believed could host microbial life. The loss of Jupiter means the loss of these moons as well, and with them, the potential for one of the most profound discoveries in history: extraterrestrial life. Future missions that had been in planning stages: robotic landers, subsurface, ocean probes, atmospheric balloons, must now be reimagined or abandoned altogether. The infrastructure of exploration that was slowly forming around Jupiter vanishes along with the planet, beyond science and propulsion. Jupiter's absence also forces a philosophical reckoning. For millennia, Jupiter has been a constant presence in the sky, a brilliant wanderer, a glowing orb that captivated astronomers from Babylon to Galileo. Its sudden disappearance challenges humanity's sense of permanence in the cosmos. If a world so massive can vanish, what does that say about our place in this universe? On a practical level, the shift affects planetary protection protocols as well. Jupiter's gravity helped limit the migration of potentially dangerous objects into Earth-crossing orbits. With that natural filter gone, space agencies must devote more resources to asteroid and comet detection, building new early warning systems, expanding deep sky monitoring, and developing interception technologies. This ushers in a new era, one of defensive space engineering. Humanity, now more exposed, begins to accelerate programs focused on planetary defense. Space-based infrared telescopes are launched to detect dark objects approaching from the outer solar system. New propulsion systems are tested: nuclear thermal engines, solar sails, and even early ion drives designed to reach dangerous objects faster and with greater flexibility than ever before. Paradoxically, Jupiter's absence becomes a catalyst for technological growth. What was once a passive dependence on a natural protector evolves into active preparation. The era of trusting the cosmos to care for us gives way to an era of vigilant guardianship. And this shift reaches into human psychology. The stars still shine, but one is missing. Children born in this new era never see Jupiter in the night sky. They grow up learning of its existence only through images and simulations. It becomes a ghost of science, a lesson in celestial impermanence. For many, it becomes a symbol of both loss and inspiration. The universe is vast and fragile, and our place within it demands curiosity, humility, and vigilance. Perhaps, in time, this awareness leads to even greater things. A new focus on interstellar travel emerges, with Jupiter no longer serving as a key to the outer solar system, humanity begins to look beyond entirely. Missions to nearby star systems, such as Alpha Centauri, gain momentum. Jupiter's absence, while a loss, becomes a spark, an invitation to push farther, think bolder, and embrace the unknown more fully than ever before. In the next chapter, we'll explore the solar system's long-term evolution in this new configuration. What happens in 10 million years, 100 million, without Jupiter's stabilizing mass? Will planetary orbits remain predictable? Will they begin to cross, drift, and ultimately dissolve into chaos? Chapter 8. The clock unwinds. Long-term instability in a Jupiterless system. At first glance, the solar system remains intact. The sun still burns, planets still orbit, and moons still circle their primaries. But remove a keystone, and the arch may stand for a while until, one day, it doesn't. The disappearance of Jupiter was not an explosion, nor a collision. It was an erasure, quiet and instantaneous. Yet its absence sets in motion a sequence of changes that stretch across millions, tens of millions, even hundreds of millions of years. This is the slow unwinding of cosmic order. Our solar system, once thought to be a clockwork of near-eternal regularity, begins to show signs of gravitational wear. The orbits of planets, once stable, thanks in part to Jupiter's overwhelming gravity, begin to drift. Not in dramatic spirals or sudden expulsions, but through gradual variations in eccentricity, inclination, and precession. These orbital elements define the shape, tilt, and wobble of each planet's path. Normally, these variations are constrained by mutual gravitational tugs. Jupiter, with its enormous mass, served as a powerful governor in this dynamic system. Its pull helped to regularize the long-term behavior of orbits, especially among the inner planets and the asteroid belt. Now, stabilizing force is gone. One of the earliest and eeriest signs of change. These models, already complex, begin to show a future where planetary orbits grow increasingly erratic. Earth and Mars, for instance, once maintained a safe distance thanks to orbital resonance and Jupiter's indirect regulation. Without that influence, their orbits slowly shift toward greater eccentricity. In 10 million years, the changes are subtle. In 100 million years, the system looks stranger. Earth's orbit elongates, Mars drifts outward. Venus and Mercury begin to feel the compounded effects of solar tides, general relativistic precession, and increasingly chaotic gravitational interactions with one another. Mercury, the smallest and closest to the Sun, becomes particularly vulnerable. Its orbit is already eccentric and sensitive. Overextended timescales, simulations show that it may one day experience a close approach with Venus or even be ejected from the solar system entirely. The probability is low, but without Jupiter anchoring the inner planets, the margins for chaos grow thinner. There is also a cumulative gravitational coupling between Saturn, Uranus, and Neptune. Jupiter once provided a counterbalance to their interactions. Now, their mutual tugs go unchecked, and small imbalances amplify over eons. Saturn's orbit, slowly shifting due to resonance with Uranus, may push that planet into new configurations, either inward, toward the asteroid belt, or outward, toward the edge of the solar system. This chain of orbital reshuffling also affects their moons. Moons like Titan, Enceladus, Miranda, and Triton are sensitive to the orbital behavior of their host planets. A shift in the host's orbit or axial tilt can alter tidal heating within the moon, destabilize resonant moon systems, or even eject smaller moons from stable orbits. Over tens of millions of years, the elegant clockwork of moon resonances begins to dissolve. Some moons may crash into their planets. Others may be expelled into interplanetary space, becoming rogue satellites of the Sun. The asteroid belt also enters a period of prolonged instability, with Jupiter no longer clearing resonant gaps and sweeping away unstable orbits. More chaotic interactions take place. Some larger asteroids coalesce, but many fragment. Over time, gravitational interactions with Mars, Earth, and Saturn send more fragments inward. This sustained bombardment increases the likelihood of extinction-level impacts on the inner planets no longer protected by Jupiter's deflection. One particularly haunting possibility lies in orbital resonance overlaps. As planetary orbits slowly shift, their gravitational influences can begin to interfere with each other, amplifying instead of damping oscillations. This kind of overlapping resonance is a key driver of chaos in unbodied systems. Over vast timescales, it could lead to a crossing of orbits, an event that would have been vanishingly unlikely with Jupiter in place. Imagine a distant future where Mars and Earth's paths intersect at certain points in their respective orbits. Even a close approach could trigger massive tidal disruptions or atmospheric perturbations. Not immediate catastrophe, but a dangerous flirtation that destabilizes both worlds further and beyond the planets. The Sun is changing to dot as it ages. The Sun slowly increases in luminosity. In 500 million years, Earth may no longer be habitable due to a runaway greenhouse effect. Jupiter's gravitational presence would not have changed this reality, but its absence ensures that Earth enters this phase with even greater orbital instability and increased likelihood of cometary or asteroidal threats. The ultimate fate of the solar system, billions of years from now, was always destined to be dissolution. The sun will swell into a red giant, engulfing Mercury, Venus, and possibly Earth. But with Jupiter gone, this disintegration may arrive sooner or unfold more violently. Some simulations suggest that a Jupiterless solar system is more prone to early ejections of planets, particularly smaller ones like Mercury or even Mars. Other planets may become rogue, flung into interstellar space after chaotic gravitational encounters. The solar system, once a tightly knit family of worlds, may end as a scattered diaspora of exoplanets and orphan moons drifting silently through the dark. This is the slow poetry of celestial decay. It reminds us that nothing in the universe is truly permanent. Even systems that feel timeless are, in truth, delicately balanced acts of gravity and motion. Remove one key stone, especially one as massive as Jupiter, the stage begins to change, and yet life may still persist for billions of years. Earth may still support civilizations long after Jupiter's absence is noticed. The chaos is not immediate, but its seeds are sown. The solar system becomes a place of evolving complexity, increasingly unpredictable, increasingly alive with motion. In the next chapter, we'll shift from orbits and gravitational mechanics to something more personal: how humanity might interpret and adapt to the disappearance of Jupiter, both culturally and psychologically. For when something so vast vanishes, it changes not only the stars, but also our sense of cosmic security. Chapter 9: The Vanishing Giant. Humanity's Psychological Reckoning. In the immensity of the cosmos, the planets are ancient companions, fixed presences in the sky, known since before recorded history. Among them, Jupiter was always something more: a glowing sentinel in the night, a massive protector, and a source of both wonder and mythology. Its disappearance, though physical and gravitational, would send ripples through the human psyche, as deep and far-reaching as those in space itself. At first, there is disbelief in observatories across the world. Scientists point telescopes toward where Jupiter should be, only to find nothing. No blur of atmospheric bands, no moons casting shadows across its face. Just empty space, quietly mocking centuries of expectation. News spreads quickly. Jupiter has vanished, not imploded, not exploded, simply gone. Humanity, wired to seek meaning, reacts not just with scientific urgency, but with existential dread. This wasn't just a planet, it was a presence. For millennia, Jupiter held symbolic weight: the king of gods to the Romans, the thunder bearer of myth. Its loss echoes in the cultural subconscious as a fracture in cosmic order. Religions respond in their own ways. Some interpret it as a sign of change, of endings, of divine intervention. Others see it as proof of the fragile nature of all creation. Philosophers speak of impermanence. Poets write of empty skies. Artists depict Earth not as a world within a solar system, but as a lonely traveler now missing a guardian. And then comes the scientific scramble. Was this an act of nature or something more? Telescopes scanned for signs of disruption, gravitational wakes, displaced moons, energy anomalies. Probes and satellites attempt to analyze the gap. The international scientific community rallies to study the event, publishing theories ranging from spontaneous collapse to exotic matter anomalies, or even intervention by unknown intelligences. But one thing becomes clear: the planet is gone, and Earth is more vulnerable than ever. In classrooms, textbooks are rewritten, astronomical charts updated. Children growing up after the event will never see Jupiter in the sky. They will learn of it as we learn of lost species through pictures, simulations, and the whispered reverence of something once alive. This shift in perspective leads to profound cultural revaluation. Jupiter was not just a planet, it was a concept, a symbol of scale. Its disappearance changes the way humanity sees the universe. It forces a realization: the cosmos is not immutable. If something so massive, so seemingly eternal, can be lost, then nothing is beyond change. Not the stars, not even the planets. Some respond with fear, others with awe. The philosophical implications stir new movements in thought. Cosmic fatalism grows humans recognizing the smallness of their existence amid such grand volatility. Others become cosmic optimists, seeing the event as a wake-up call to expand outward, to secure life beyond Earth, to never again be caught unaware by forces greater than our comprehension. Space exploration surges with new urgency. Plans to settle Mars, construct lunar bases, or develop deep space stations take on added emotional weight. Not just projects of ambition, but of survival. If the universe can change without warning, then humanity must adapt, innovate, and migrate or risk vanishing like Jupiter. In parallel, a new mythology is born. Just as ancient peoples once invented stories to explain the stars, modern culture begins to craft narratives around Jupiter's vanishing. Books, films, and digital experiences explore the mystery. Was it natural? Was it a message? Was it a test? Conspiracy theories flourish, but so do visions of wonder. Some imagine Jupiter as having ascended to a higher state, transformed into a different kind of celestial being. Others suggest it slipped through a rift in space-time, now orbiting a star in another dimension. Science fiction embraces the narrative wholeheartedly. Jupiter's moons, once part of its majestic family, become relics adrift. Europa, now a moon without a planet, becomes a symbol of resilience. Ganymede, largest of all moons, is reimagined as a drifting world waiting to be claimed. Humanity begins to send probes and stations to these orphaned moons, not only to study them, but to honor what was lost. Some communities, both digital and physical, begin holding annual nights of remembrance. When Jupiter should be visible in the sky, people gather under the stars. They light lanterns, project holograms of the planet, and share stories. Astronomers present lectures. Artists display images of what Jupiter meant to storms, its stripes, its moons. These rituals become a way to cope, to connect with each other, and to reaffirm our place in a shifting universe. And then, quietly, a strange kind of acceptance begins to grow, as, with all loss, time dulls the pain. Humanity adapts to a sky without Jupiter. Future generations learn to navigate a world where planetary permanence is no longer assumed. There is grief, yes, but also growth. Jupiter's absence becomes part of humanity's collective mythology, reminder that the universe is dynamic, not static. In the process, Earth's gaze turns outward more than ever, not just in search of explanations, but in search of connection. We begin to see the cosmos not as a distant backdrop, but as a living theater of forces we do not yet fully understand. In the next chapter, we return from the human heart to the cosmic scale, looking at how Jupiter's absence affects the Sun itself, the solar wind, and the heliosphere. For even the star at the center of everything begins to feel the subtle change in its orbiting entourage. Chapter 10: The Sun's Quiet Response, Heliosphere, and Solar Wind. Without Jupiter at the heart of our solar system burns a vast furnace of nuclear fusion. The Sun, its radiant energy, bathes the planets, shaping climates, fueling life, and driving complex planetary phenomena. But the Sun's influence extends far beyond light and heat, continuously emits a steady stream of charged particles known as the solar wind. This wind forms a vast dynamic bubble in space called the heliosphere, a protective shield enveloping the solar system and carving out a region of space dominated by the Sun's magnetic field and plasma flow. The heliosphere is our solar system's frontline defense against the relentless bombardment of high-energy cosmic rays and interstellar matter. Its shape and size are determined by a delicate balance between the outward pressure of the solar wind and the inward push of the interstellar medium, the sparse gas and dust that fill the space between stars. Jupiter, though a planet, exerts a surprising influence on this vast bubble. Its immense gravity sculpts the paths of charged particles in the outer solar system. Jupiter's magnetosphere, the largest and most powerful planetary magnetic field in the solar system, extends millions of kilometers into space, creating a complex region where solar and planetary magnetic fields interact. These interactions produce shock waves, magnetic reconnections, and plasma flows that ripple outward and influence the solar wind structure, with Jupiter's sudden disappearance. This intricate dance changes dramatically. First, the magneto-hydrogenic environment of the outer solar system shifts, without Jupiter's vast magnetosphere acting as a deflector and modulator. The solar wind flows more freely into previously shielded regions. This alters the pressure distribution within the heliosphere, potentially causing it to lose its symmetry. Instead of the near spherical shape maintained by the interplay of solar and planetary forces, the heliosphere may become elongated or irregularly shaped. This asymmetry can have subtle but far-reaching consequences. The boundary of the heliosphere, called the heliopause, marks the edge of the Sun's magnetic dominance. Beyond it lies the interstellar medium, a turbulent sea of cosmic rays, interstellar gas, and dust. If the heliopause moves inward due to altered solar wind pressure, this protective shield shrinks, exposing the solar system to higher fluxes of cosmic rays. An increased cosmic ray flux can affect planetary atmospheres in various ways. High-energy particles interact with atmospheric molecules, generating ionization, chemical reactions, and sometimes influencing cloud formation. On Earth, this could translate into subtle shifts in climate patterns over geological timescales. Moreover, increased cosmic radiation poses direct risks to life and technology. Radiation doses at high altitudes and in space increase, impacting satellites, astronauts, and even the electronic systems of space probes. Without Jupiter helping to shape the heliosphere and deflect charged particles, space weather events might become more intense or unpredictable. The need for advanced radiation shielding in spacecraft and on Earth becomes paramount. But the influence of Jupiter's absence is not limited to magnetic and plasma interactions. Jupiter's massive gravity caused the Sun to orbit a point known as the barycenter, the center of mass of the solar system, which lies just outside the Sun's surface. This orbital motion results in a subtle wobble of the Sun itself, completing a cycle approximately every 11.9 years, the same period as Jupiter's orbit. This wobble is believed to be linked, at least in part, to variations in solar activity cycles, including the rhythm of sunspot appearance and magnetic field reversals, while the precise mechanisms remain an active field of study. Removing Jupiter's gravitational pull alters this dance. Without Jupiter, the Sun's barycentric motion simplifies. The solar wobble lessens, potentially affecting the timing and intensity of the solar magnetic cycle. Changes in this cycle influence solar flare frequency, coronal mass ejections, and the overall behavior of space weather. Although these changes would be subtle, their cumulative effects could alter conditions in the inner solar system, influencing planetary magnetospheres, atmospheric chemistry, and the radiation environment. Looking further outward, the Earth cloud, the vast spherical shell of icy bodies at the edge of the Sun's influence, feels the ripple effects as well. The heliosphere's shape and strength affect how interstellar medium particles and galactic cosmic rays interact with these distant objects. Changes in solar wind pressure and magnetic field topology can influence the rate at which comets are nudged inward, feeding into the long-term dynamics of cometary influx into the inner solar system. This interconnection completes a feedback loop. Jupiter's disappearance destabilizes the heliosphere, which in turn affects the influx of cometary bodies, objects that Jupiter once helped to shield Earth from by gravitationally deflecting or capturing them on a cosmic timescale. These changes to the Sun's protective bubble will contribute to a more dynamic and potentially hazardous space environment. The solar system, once shielded by a finely tuned balance of planetary and solar forces, begins to open itself to the greater galactic environment. Yet, amidst these transformations, the Sun remains the unchanging heart of the system, its nuclear fires burning steadily. The interplay of forces, gravity, magnetism, plasma flows continues, reshaped by the absence of its greatest planetary companion. This quiet loss of a single node resonates throughout the whole dot. In the next chapter, we will delve into the fate of the solar system's smallest and most numerous members, the asteroids, meteoroids, and cosmic dust, and explore how their journeys and behaviors are transformed in this new Jupiterless era. Chapter 11: The Untamed Swarm, Asteroids, Meteoroids, and Cosmic Dust in a Jupiterless Solar System. Among the vast majesty of the planets and moons, the solar system's smallest inhabitants, asteroids, meteoroids, and dust particles play crucial yet often overlooked roles in its dynamic evolution. Though diminutive in size, their collective mass and sheer numbers make them vital actors in the gravitational drama shaped by Jupiter's presence. With the gas giant gone, these countless fragments find their orbits and behaviors altered in profound ways, unleashing a cascade of consequences that ripple from the asteroid belt inward to Earth and beyond. The asteroid belt, located between Mars and Jupiter, was long kept in check by Jupiter's powerful gravity. Its presence carved out the belt's intricate structure, sculpting gaps known as Kirkwood gaps, and ejecting or capturing unstable asteroids. Jupiter acted as both a guardian and gatekeeper, shepherding this swarm of rocky bodies and preventing many from straying into the inner solar system. Without Jupiter's gravitational oversight, the asteroid belt begins to unravel. The resonant orbits that once maintained relative stability become chaotic. The absence of Jupiter's massive tug allows smaller gravitational interactions from Mars, Saturn, and even passing comets to disturb asteroid paths more freely. Over time, this instability causes an increase in the number of asteroids nudged inward toward the terrestrial planet. This influx raises the odds of impact events on Earth and its neighbors, threatening biospheres and civilizations. Though large, catastrophic impacts remain rare, the background rate of smaller collisions and meteor showers would increase noticeably. Meanwhile, the population of near-Earth objects unknown swells. Many of these bodies, previously trapped or deflected by Jupiter's gravity, now drift on paths crossing Earth's orbit with greater frequency and unpredictability. Meteor showers intensify, with more frequent bright fireballs streaking across the sky. Space agencies around the world ramp up asteroid detection and tracking programs, striving to forecast potential impacts with greater urgency. Beyond the asteroid belt lies the vast expanse of the Kuiper belt and the distant Oort cloud repositories of icy bodies and comet nuclei. Jupiter's absence destabilizes the intricate gravitational balance that had limited the migration of some comets. Inward, more long-period comets begin to enter the inner solar system, appearing unpredictably from distant reaches. The increased cometary flux poses additional hazards, but also scientific opportunities. Comets are time capsules, preserving pristine materials from the solar system's birth. Cosmic dust, too, undergoes transformation, the continual collisions within the asteroid belt and Kuiper belt generate fine particles that drift slowly inward, carried by the gentle push of solar radiation pressure. Jupiter's gravity once influenced dust migration patterns and densities in various regions, creating dust bands and shaping the zodiacal light, the faint glow visible along the ecliptic. Without Jupiter, dust distributions become more irregular, potentially affecting observations and altering the micrometeoroid environment encountered by spacecraft. On Earth, the increased flux of dust and meteoroids influences the upper atmosphere, leading to brighter noctilucent clouds and altering ionospheric conditions. These changes have subtle but detectable effects on communication and navigation systems. The Moon and other airless bodies, exposed to higher impact rates, accumulate more craters, offering future geologists a record of the solar system's altered dynamism over millions of years. This more chaotic environment could have profound implications for planetary evolution, habitability, and the survival of life. Yet, amid this untamed swarm, the dance of gravity continues, reshaped but persistent. The solar system adapts to the loss of its largest guardian by becoming more volatile, more dynamic, and more unpredictable. In the following chapter, we will explore how this increased dynamism affects the smaller moons and ring systems of the remaining planets, and how their delicate balances might shift in the absence of Jupiter's stabilizing influence. Chapter 12: Moons and Rings. Delicate balances without Jupiter's watch. Jupiter's grandeur extended far beyond its own massive body. Its powerful gravity shaped the orbits of countless moons and even influenced the ring systems of neighboring planets. With Jupiter gone, the intricate gravitational ballet performed by moons and rings across the solar system begins to falter, leading to subtle but far-reaching changes in their stability and evolution. Among the most affected are the moons orbiting the giant planets Saturn, Uranus, and Neptune. These gas and ice giants each possess their own intricate families of moons, many locked into resonant orbits, gravitationally synchronized patterns where orbital periods maintain simple ratios. These resonances help stabilize their orbits, preventing collisions or chaotic drifting. Jupiter's disappearance alters the gravitational landscape in which these giants and their satellites reside, without Jupiter's massive pull helping to balance gravitational interactions. The orbits of these planets themselves begin subtle shifts over long timescales. These planetary shifts cascade down to their moons. Saturn's majestic moons, Titan, Enceladus, Rhea, and dozens more are particularly sensitive to such changes. Titan's thick atmosphere and Enceladus's famous water plumes depend on internal tidal heating, generated by orbital resonances. If the orbits shift enough, the tidal flexing could diminish or intensify unpredictably, altering geological and potentially biological processes. Similarly, Uranus's moons, locked in delicate gravitational dances, could experience perturbations that destabilize their orbital resonances. Miranda, known for its fractured surface suggesting past upheavals, may undergo renewed tidal stresses or orbital shifts. Neptune's moons, including the retrograde Tritona captured Kuiper belt object, could feel destabilized, Triton's unusual orbit already suggests past orbital evolution and tidal interaction. Without Jupiter's stabilizing presence in the broader system, these interactions may intensify beyond moons. The solar system's ring systems face their own challenges. Saturn's rings, the most spectacular and complex, are maintained by a balance of gravitational forces between the planet, its moons, and the ring particles themselves. The shifting gravitational environment may alter the orbits of shepherd moons that confine the rings, leading to changes in ring structure, density waves, and potentially ring erosion or spreading. Uranus and Neptune, with their more subtle ring systems, might see increased instability as well, with ring particles subject to altered resonances and gravitational perturbations closer to the Sun. The rings of the minor planets and debris disks around smaller bodies, like the tenuous ring around Chariklo, so experience indirect effects. Increased fluxes of dust and meteoroids could replenish or erode these delicate features more rapidly in a destabilized solar environment. Even Earth's moon, long considered stable, is not entirely immune. Jupiter contributed to the overall gravitational balance of the inner solar system, subtly influencing Earth's orbit and axial tilt. Changes in Earth's orbit and spin may affect tidal interactions with the Moon, potentially altering its recession rate or orbital eccentricity over geological timescales. These combined effects illustrate that moons and rings are not isolated entities, but integral parts of the solar system's gravitational web-sensitive indicators of its changing architecture. The loss of Jupiter thus triggers a cascade of adjustments. Moons may drift into new orbits, resonance patterns could break, tidal heating varies, and ring systems evolve unpredictably. This complex, slow-moving transformation echoes throughout the solar system, reminding us that even the smallest celestial bodies depend on the gravitational might and presence of giants like Jupiter for their stability. In the next chapter, we will investigate the implications for Earth's climate and biosphere, as this broader gravitational shift unfolds over millennia and beyond. Chapter 13: Earth's Changing Climate and Biosphere. The ripple effects of a missing giant. Earth's climate and biosphere are products of a complex interplay of forces: solar energy, atmospheric chemistry, ocean currents, and gravitational influences, both near and far. Among these gravitational factors, Jupiter has long played a subtle but significant role in shaping Earth's environment, stability, and, by extension, the conditions that sustain life. With the disappearance of Jupiter, these dynamics face profound and far-reaching consequences, unfolding over millennia and beyond. Orbital variations and climate cycles. Earth's orbit is not a fixed ellipse, but a slowly evolving path influenced by the gravitational tugs. These variations, known collectively as Milankovitch cycles effect, Earth's climate by altering the distribution and intensity of sunlight reaching its surface. Jupiter's massive gravity has contributed to stabilizing Earth's orbit, keeping variations in eccentricity, axial tilt, obliquity, and precession within bounds that support long-term climate stability. Without Jupiter, simulations suggest these orbital parameters begin to drift more erratically over tens of thousands to hundreds of thousands of years. Earth's eccentricity could increase, leading to more pronounced differences between perihelion, closest approach to the Sun, and aphelion, farthest distance. This change would amplify seasonal contrasts, potentially intensifying ice ages and warm periods, or conversely, creating extreme climate swings that challenge ecosystems. Similarly, Earth's axial tilt may become less stable. Currently, the Moon and Jupiter work in tandem to regulate Earth's obliquity, maintaining it within a narrow range around 23.5 degrees. Without Jupiter's gravitational pull, this tilt could vary more widely, oscillating between extremes over geological timescales. Increased axial tilt variability would dramatically affect climate zones, seasonal weather patterns, and even the length of day and night cycles. Extreme tilts could cause polar regions to receive more direct sunlight seasonally, disrupting ice caps and ocean circulation. Impact on ocean currents and atmospheric dynamics. Climate is further modulated by oceanic and atmospheric circulation. Systems complex networks driven by solar heating, Earth's rotation, and planetary scale forces as Earth's orbit and tilt vary. So too do patterns of solar insolation that drive the global climate engine. Changes in these parameters could alter the strength and direction of major ocean currents, like the Gulf Stream and the Antarctic Circumpolar Current. Altered ocean currents impact heat distribution, nutrient cycling, and carbon sequestration in the oceans, influencing atmospheric CO2 levels and global temperatures. This feedback loop could accelerate climate change, destabilize weather systems, and disrupt habitats. Biosphere adaptations and evolutionary pressures. Life on Earth has always adapted to gradual environmental changes. However, the increased variability and extremes induced by a destabilized orbit could place additional evolutionary pressures on species and ecosystems. Habitats may shift geographically as temperature zones migrate. Some species could face extinction due to habitat loss or climate stress, while others adapt or migrate to new niches. Rapid climate swings could favor opportunistic and generalist species, reducing biodiversity in the long term, increased impact, risk, and its ecological effects beyond climate. Earth faces heightened risk from impacts, with Jupiter no longer shielding the inner solar system. Increased asteroid and comet influx raises the likelihood of collision events. Large impacts can trigger global environmental catastrophes, massive wildfires, atmospheric dust blocking sunlight, acid rain, and climate disruption. Such events have shaped Earth's biological history, including the mass extinction that ended the reign of the dinosaurs. A higher frequency of smaller impacts could result in more localized but cumulative ecological damage, challenging recovery and ecosystem resilience. Potential human responses and adaptations. Human civilization, with its technological and scientific advancements, may mitigate some of these risks. Climate engineering, asteroid deflection programs, and habitat management could help buffer the planet's environment. However, the underlying gravitational shifts remain a fundamental driver of Earth's climate dynamics. Understanding and adapting to these new realities would become an essential part of humanity's long-term survival strategy. Philosophical and cultural reflections. The knowledge that a missing planet influences Earth's very climate and life invites a humbling perspective. It highlights the fragility and interconnectedness of the solar system and the deep ties between cosmic events and life on a small blue planet. Jupiter's absence is a cosmic reminder. Our planet is not isolated, but a part of an intricate celestial network where change in one place resonates everywhere. Chapter 14: Navigating the Void, Human Technology and Space reshapes not only the celestial mechanics of our solar system, but also humanity's endeavors to explore, understand, and inhabit space. As the solar system's largest planet vanishes, the technologies, mission plans, and ambitions of space exploration face unprecedented challenges and new opportunities. Gravity assists in mission planning for decades. Jupiter has been a linchpin in interplanetary travel. Its immense gravity provided spacecraft with powerful slingshots, dramatically reducing the fuel, time, and cost required to reach distant planets and beyond. The Voyager, Galileo, Cassini, Juno, and many other missions relied on Jupiter's gravity assists. With Jupiter gone, mission planners must rethink trajectories. Without the option of Jupiter's gravitational boost, missions to the outer planets and Kuiper Belt require either significantly more fuel or acceptance of much longer travel times. This shift challenges current propulsion technologies and could delay or cancel planned missions. To compensate, space agencies accelerate the development of advanced propulsion systems, nuclear, thermal rockets, ion drives, solar sails, and even speculative fusion engines. These technologies aim to reduce dependence on gravity assists, enabling missions with greater autonomy, increased hazardous object detection as Jupiter's protective role diminishes. Earth faces heightened risks from asteroids and comets. This drives urgent investment in planetary defense infrastructure, space-based infrared telescopes, early warning systems, and deflection technologies such as kinetic impactors and gravity tractors. International cooperation intensifies, forming alliances and treaties dedicated to asteroid monitoring and impact prevention. This global effort marks a paradigm shift. Space exploration expands from discovery to active defense. Scientific opportunities and challenges, the loss of Jupiter itself becomes a unique scientific frontier. Understanding the mechanisms behind its disappearance drives new theories in astrophysics and planetary science. Are there exotic phenomena yet undiscovered? Is this an unprecedented cosmic event or part of a hidden cosmic cycle? Probes and observatories focus on the space where Jupiter once orbited, searching for clues, remnants of its atmosphere, displaced moons, or new gravitational anomalies. Missions to the orphaned Galilean moons become high priority. Despite increased technical challenges, the push toward interstellar exploration, with the outer solar system less accessible via traditional means, humanity's gaze turns beyond concepts. For interstellar probes, such as the breakthrough Starshot initiative, gain momentum. The goal: to send miniature laser-propelled spacecraft to nearby stars within decades, pioneering the first steps beyond the solar system. This shift inspires innovation in materials science, miniaturization, and autonomous systems, fostering technologies that will also benefit terrestrial applications. Economic and cultural impacts: the changed landscape affects commercial space ventures, satellite deployment, and the burgeoning space economy. Increased mission costs may slow some projects, but inspire novel solutions, like asteroid mining closer to Earth or new orbital infrastructure. Culturally, the absence of Jupiter symbolizes a new era, one of heightened awareness about cosmic fragility and humanity's responsibility as stewards of both Earth and space, preparing for the unknown. Ultimately, the disappearance of Jupiter forces humanity to embrace uncertainty. It highlights the need for flexibility, resilience, and visionary thinking in technology development and exploration strategy. The void left by Jupiter is both a challenge and an invitation, prompting humankind to innovate, adapt, and reach further than ever before. Chapter 15: The Lost Moons. The fate of Jupiter's satellites. Jupiter's disappearance did not merely erase a planet. It dissolved an entire system of moons, each with its own unique characteristics, mysteries. The fate of these celestial companions, the famous Galilean moons, smaller, irregular satellites, and countless minor moons, as a complex story of orbital chaos, capture, and dispersal that unfolds over millennia. The Galilean moons, Europa, Ganymede, Callisto, and Io, the four largest moons of Jupiter, are among the most fascinating worlds in the solar system. Europa's icy crust conceals a subsurface ocean that might harbor life. Ganymede is the largest moon in the solar system and possesses its own magnetic field. Io is a volcanically active world, and Callisto bears an ancient, heavily cratered surface when Jupiter vanishes. These moons lose their primary gravitational anchor. In an instant, their carefully balanced orbits transform into trajectories around the Sun, turning from satellites into independent minor planets or small bodies orbiting the Sun directly. Initially, their orbits resembled Jupiter's former path, traveling roughly in the same region of space. However, lacking Jupiter's gravitational pull to maintain their synchronized orbits and mutual resonances, the moon's paths diverge over time. Their mutual gravitational interactions, previously orchestrated by Jupiter's dominance, now lead to slow but growing orbital shifts, orbital dispersion, and potential collisions without Jupiter. The moons risk collisions either with each other or with other solar system bodies. Europa and Ganymede, for example, may drift closer together, potentially crossing paths. Over millions of years, the chaotic orbital evolution could lead to impacts, mergers, or ejections. The moons may also face the threat of capture or perturbation by other planets, particularly Saturn, which lies relatively close in the outer solar system. Some moons could be gravitationally pulled into new orbits around Saturn or even Mars or Earth. Though such captures would be rare and complex, others might become rogue objects, drifting alone in heliocentric orbits that could eventually cross Earth's path, raising impact risks. The smaller and irregular moons Jupiter's numerous smaller and irregular moons, often captured asteroids or comets themselves, face even more unpredictable futures. Their tenuous orbits around Jupiter depended heavily on the planet's gravity. Without it, they scatter into space. Some of these bodies become part of the broader population of small solar system bodies, joining the ranks of asteroids and Kuiper Belt objects. Others may be ejected entirely, hurtling into interstellar space as rogue minor planets. Scientific and exploration implications, though. Loss of Jupiter's moons as stable satellites complicates scientific exploration plans. Missions aimed at studying Europa's ocean or Io's volcanism face new challenges. With orbits no longer stable or predictable, nonetheless, the moons become compelling targets in their own right as newly independent worlds with evolving orbits. Histories marked by sudden freedom and potential for discovery as they traverse the solar system. Symbolic loss and cultural impact for humanity. Jupiter's moons are not just scientific curiosities, they are symbols of exploration and wonder. Their fate stirs imagination and reflection on impermanence and cosmic change. Communities dedicated to astronomy and planetary science mourn the loss and rally to study these wandering worlds, preserving their legacy through observation, modeling, and storytelling. Chapter 16: The Outer Solar System. A new landscape without Jupiter. The outer solar system, a vast and cold realm beyond the asteroid belt, is a dynamic environment dominated by the gas giants and icy bodies of the Kuiper Belt and Oort cloud. Jupiter's sudden disappearance sends shockwaves through this region, reshaping the architecture and behavior of its distant denizens in profound and lasting ways. Saturn's shifting domain. Saturn, the solar system's second largest planet, has long existed under Jupiter's gravitational shadow. The loss of Jupiter alters the balance of power among the giant planets, allowing Saturn's gravitational influence to expand and evolve. Over thousands to millions of years, Saturn's orbit experiences subtle shifts, potentially moving slightly closer to the Sun or adopting a more eccentric path. These changes impact the planet's numerous moons and ring systems, as detailed in previous chapters, but also affect the distribution of small bodies in the outer solar system. Saturn may capture some former Jovian moons, altering their orbital characteristics and adding new complexity to its satellite system. Conversely, some objects once stabilized by Jupiter's gravity become destabilized, wandering into chaotic orbits that may cross Saturn's path. The Kuiper Belt, an unsettled frontier. The Kuiper Belt, home to dwarf planets like Pluto, Haumea, and Makemake, is a vast reservoir of icy bodies orbiting the Sun beyond Neptune. Jupiter's role as a gravitational gatekeeper helped maintain relative order in this region by influencing the orbits of scattered disk objects and shepherding bodies through mean motion resonances. With Jupiter gone, the Kuiper Belt becomes more dynamically unstable. Some objects previously held in resonant orbits may be nudged into new trajectories, increasing the rate at which they migrate inward toward the inner solar system as comets. This migration increases the flux of icy bodies entering the inner solar system, posing both hazards and scientific opportunities. More comets brighten Earth's skies unpredictably, and their impact risk rises. Yet, these comets also offer pristine material from the solar system's formation, ripe for study. ORT, cloud disturbances. Far beyond lies the Oort cloud, a vast spherical shell of icy bodies that marks the boundary of the Sun's gravitational influence. Jupiter's immense gravity helps shield this cloud from perturbations by passing stars and galactic tides. Without Jupiter, the Oort cloud structure becomes more vulnerable to these external forces. More comets may be dislodged, increasing the long-period comet influx toward the Sun. Implications for future exploration. The outer solar system, already challenging to explore, grows even more complex. Space missions must account for the shifting orbits and increased hazards posed by wandering small bodies. Yet, the evolving environment offers unprecedented scientific prospects. Tracking the changing dynamics of Kuiper Belt objects and comets provides insights into planetary formation, solar system evolution, and the effects of large-scale gravitational change. Cosmic perspective. Jupiter's disappearance reveals the fragile balance holding the solar system's outer reaches together. The giant planet's absence leaves a gap not only in mass but in stability, prompting a redefinition of the cosmic landscape. This new, unsettled frontier challenges humanity's understanding and invites ongoing exploration to unravel the mysteries that emerge from the void left behind. Chapter 17. The Solar System's Future. Long-term evolution. Without Jupiter, the disappearance of Jupiter initiates a slow but inexorable transformation of the solar system's architecture. While immediate effects are profound, it is over millions to billions of years that the full consequences of the gas giant's absence unfold, reshaping the destiny of planets, moons, and small bodies in ways both subtle and dramatic. Orbital instabilities and planetary chaos. Jupiter's massive gravity has long served as a stabilizing force in the solar system, regulating the orbits of its planetary neighbors and maintaining a delicate balance. Without this anchor, the orbits of planets, especially the outer giants Saturn, Uranus, and Neptune, begin to shift over geological timescales. Simulations of a solar system without Jupiter reveal an increase in orbital eccentricities and inclinations, making planetary paths more elliptical and tilted. These changes heighten the chances of close encounters between planets, which could, over vast time, result in collisions, ejections from the solar system, or new orbital resonances. Impacts on the inner planet's Earth and its terrestrial siblings Mercury, Venus, and Mars are not immune. Altered gravitational forces cause small but cumulative changes in their orbits, potentially impacting climate stability. Axial tilt and orbital resonance with one another. In extreme scenarios, millions of years in the future, the risk of planetary collisions or destabilization increases, though such events remain unlikely within human timescales, small body populations, and collision cascades without Jupiter. To shepherd and eject many small bodies, the population of asteroids, comets, and debris in the inner solar system grows. This increased population raises collision rates, potentially leading to a cascade of impacts and fragmentation that further increases dust and debris densities. The resulting environment challenges planetary atmospheres and magnetospheres, increasing radiation, exposure, and surface hazards, solar evolution, and planetary habitability. As the Sun ages, it will expand into a red giant in several billion years. The destabilized solar system dynamics could influence how planets respond to this transformation, altering potential habitability, windows, and planetary fates. Humanity's role in a changing solar system, the distant future. Humanity, or its descendants, may adapt by migrating beyond Earth, colonizing other worlds or artificial habitats. Understanding and anticipating the long-term evolution of the solar system without Jupiter becomes crucial for its survival and expansion. Technological advancements might enable active planetary defense, orbit correction, or even artificial gravitational influences to mitigate instability. Philosophical reflections on cosmic change. Jupiter's absence is a testament to the universe's impermanence and dynamism. It reminds us that celestial bodies, no matter how massive or enduring, are subject to change and loss. This cosmic humility inspires awe and a renewed commitment to stewardship of Earth, of our solar system, and of our place in the vast cosmos. Chapter 18. The effects on the solar system's magnetic environment. Jupiter is not only the largest planet in the solar system by mass, but also hosts the strongest planetary magnetic field, a vast magnetosphere that dwarfs Earth's own. This magnetic giant plays a key role in shaping the magnetic and charged particle environment throughout the solar system. With Jupiter gone, the solar system's magnetic landscape experiences significant changes from the immediate vicinity of the giant planets to the interplanetary medium itself. Jupiter's magnetosphere. A magnetic giant Jupiter's magnetosphere extends up to 7 million kilometers toward the Sun and stretches far beyond its orbit on the night side, forming a magnet tail that interacts with the solar wind. It traps charged particles, electrons, and ions, creating intense radiation belts that challenge spacecraft and contribute to complex electromagnetic phenomena. This magnetic bubble influences the trajectories of charged particles in the solar wind and modulates the space environment experienced by other planets, particularly those in the outer solar system. Changes in particle flux and radiation without Jupiter's magnetosphere to trap and accelerate charged particles. the population and distribution of energetic particles throughout the solar system. Alter. Some particles previously trapped and energized within Jupiter's magnetosphere now roam more freely, increasing the flux of cosmic rays and energetic ions in the outer solar system. This enhanced radiation environment affects spacecraft instrumentation, astronaut safety, and planetary atmospheres, especially for moons and planets lacking strong magnetic fields. Impacts on the solar wind and heliospheric interactions. Jupiter's magnetic field also interacts with the solar wind, contributing to the complex structure of the heliosphere. Its absence changes the way solar wind plasma flows through the outer solar system, as discussed in earlier chapters, possibly altering shock fronts, plasma waves, and magnetic reconnection events. These changes have downstream effects on space, weather, and the magnetic environments of other planets. Influence on planetary magnetospheres. Saturn's, Uranus's, Neptune's, and Earth's experience shifts in their magnetic environments due to the changed interplanetary magnetic field conditions. The altered flux of energetic particles and solar wind plasma pressure can modify magnetospheric dynamics, including auroras, radiation belts, and magnet tail structures. Scientific and exploration considerations. Understanding these magnetic changes is critical for future missions, as the radiation environment affects spacecraft design, mission planning, and human exploration feasibility. Additionally, studying the new magnetic dynamics offers insights into planetary magnetospheres, space weather, and the fundamental physics of plasma interactions. Chapter 19. The Solar System's Barycenter. A shift in the center of gravity. The solar system is a complex gravitational dance, with bodies orbiting a common center of mass known as the barycenter. This point, located near but not exactly at the Sun's center, is influenced heavily by Jupiter's massive presence. The gas giant's disappearance causes a profound shift in the solar system's barycenter, with far-reaching consequences. Understanding the barycenter. The barycenter is the balance point where the combined mass of the Sun and planets orbit. Because Jupiter is the most massive planet, more than twice the mass of all other planets combined, exerts a dominant pull, shifting the barycenter outside the Sun's surface. At times, this causes the Sun to perform a subtle wobble as it orbits the barycenter, a motion critical to various gravitational and magnetic phenomena. Jupiter's role in solar motion. Jupiter's orbit, roughly every 11.9 Earth years, influences the Sun's path around the barycenter. This wobble affects the Sun's internal dynamics and may be linked to solar cycles, including sunspot activity and magnetic reversals. Without Jupiter, the barycenter moves closer to the Sun's center, reducing or eliminating this wobble. Consequences of the shift: the Sun's altered motion affects its internal processes, potentially influencing solar activity patterns. Changes in solar output could follow, impacting space, weather, and planetary climates. The orbits of planets, especially the gas giants, adjust over long periods due to the changed gravitational framework. This can affect orbital resonances, stability, and the overall architecture of the solar system. Implications for exoplanet detection. Understanding barycentric motion is key in detecting exoplanets by observing stellar wobbles. Jupiter's disappearance offers a natural experiment to study such dynamics and refine detection techniques. Philosophical reflection: this shift highlights the interconnectedness of celestial bodies. The loss of a single planet redefines the gravitational balance of the entire system, reminding us of the delicate harmony that sustains cosmic order. Chapter 20: The Enduring Mystery. Could Jupiter ever return? Jupiter's sudden disappearance raises profound questions, not only about the present and future of the solar system, but also about the very nature of cosmic permanence. Could such a colossal planet vanish only to return? What mechanisms could cause or reverse such an event? And what mysteries does this loss unveil about the universe? The impossibility and hypotheticals from our current understanding of physics and planetary science. A planet of Jupiter's size cannot simply vanish. Such an event would require forces or phenomena far beyond known natural laws, perhaps involving advanced astrophysical processes, unknown dimensions, or hypothetical cosmic events. Yet, pondering these hypotheticals opens the door to fascinating scientific and philosophical inquiry. Cosmic phenomena and planetary laws. Several known cosmic processes can lead to the loss or drastic alteration of planetary bodies. Catastrophic collisions, star engulfment during stellar evolution or ejection due to gravitational interactions. Could a scenario exist where Jupiter is temporarily displaced or transformed, only to return? For example, massive gravitational perturbations from passing stars or hypothetical dark matter interactions might affect planetary orbits in unexpected ways. Jupiter's moons as cosmic clues studying the fate of Jupiter. As moons and their altered orbits may offer insights into whether remnants or echoes of the planet persist. Observations of displaced moons or debris fields could hint at past or future events involving Jupiter's presence. Philosophical reflections on change and impermanence. Jupiter's loss is a powerful symbol of cosmic impermanence and transformation. It challenges assumptions about stability and invites humility before the vast and dynamic universe. It also inspires curiosity and wonder, driving humanity to explore, understand, and embrace the mysteries that shape our cosmic home. A new beginning. While the absence of Jupiter alters the solar system profoundly, it also marks the beginning of a new chapter in our understanding of celestial mechanics, planetary science, and humanity's place in the cosmos. The void left behind beckons us to explore deeper, think broader, and imagine possibilities beyond our current horizon. The story of Jupiter's disappearance is not just about a missing planet. It is about the interconnectedness of all things in the solar system. From the smallest dust particle to the sun itself, each element responds and adapts to change. In contemplating this cosmic event, we glimpse the fragile beauty and profound complexity of our celestial neighborhood. Reminder that even giants can vanish, and with them, entire worlds and destinies can shift. Yet, from this change arises opportunity to learn, to grow, and to continue our journey among the stars with renewed awe and purpose.